Welcome to section 1.5 for linear equations and inequalities. All right, example 1, we're looking at, let's see, it says solve. All right, so this first equation, let's take a look at what we have here. We have an equal sign in the middle, so it's just a regular equation. And it's just linear because x is just to the first power. So to solve this first, I'm going to go ahead and distribute to get rid of those parentheses. And then what do we have? We have 2 minus 3x minus 15 equals 14 minus x plus 3. Then I'm going to go ahead and combine like terms on both sides. Those like terms there and those like terms there. Wait, let me change color so you don't get confused. There and there. And then we have negative 3x minus 13 equals negative x plus 17. Now I'm going to get x on one side, so I'll go ahead and get x on the right side, so I'll add 3 to both sides. And then I'll move the numbers to the other side, so I'll minus the 17 from both sides. And what do I get? I get 30, so negative 30 equals 2x. Lastly, to get x by itself, we'll divide by the 2. And we're left with negative 15 equals x. And we're done. All right, let's take a look at the next equation. This one's different because it has fractions going on. But it's still just a regular equation. So my goal here is I want to get rid of the fractions first before I do anything else. So I'm going to multiply each side by a number that can hopefully cancel those denominators. What number can cancel both a 2 and a 3? 6. So we'll go ahead and multiply both sides by 6. Why do I have to multiply both sides by 6? Because that's just the rules for equations. And then when I do that, that 6 will get distributed to both of those terms. So let's write that out. That's going to be 6 times the x minus 3 over 2, plus again the 6 times 2x plus 1 over 3. Equals 24. We can simplify now, so that 6 simplifies and we're left with a 3. That 3 simplifies and we're left with a 2. So now we just have 3x, or 3 times x minus 3, plus 2 times 2x plus 1 equals 24. Again, now we're back to a problem that looks very similar to the one we had here. So the plan, distribute out to get rid of the parentheses, get variables on one side and the numbers on the other. Let's go ahead and do that. All right, then we have 3x minus 9 plus 4x plus 2 equals 24. So combining the like terms, the x's here and then the numbers here. We have 7x equals, and what's on the side? So 9 plus 2, give me negative 7. Let's go ahead and add 7 to both sides. I'm going to run out of some room here. So that'll be 7x equals, let's see, 24 plus 7. That'll give me 31. Oops, wrong color. All right, so 31. And then move that up to here. 7x equals 31. Divide both sides by 7. And what are we left with? Let's see, that cancels, and we can't simplify that any further, so that just x equals 31 over 7. Okay, so let's take a look to this here. Solutions to linear equations. So for the solutions, we could have possibly exactly one solution. We could have infinitely many solutions where they both coincide. Or we could have no solution. 2 separate lines. That's when we're setting 2 equations equal to each other, 2 equations of 2 separate lines, and seeing where they intersect. Those are the possible outcomes. So again, let's go ahead and try to solve example 2, A and B. Again, feel free to pause the video and check your answers with mine. So for this first one, again, my plan is always to get rid of those equal signs if possible. So let's go ahead and do that. That'll be 2 minus 3x plus 15 equals 14 minus 3x plus 3. Combining the like terms on each side, that'll be 3x 17 equals negative 3x plus 17 as well. Okay, oh, and then those x values cancel out. And I have negative 3x equals negative 3x. Interesting. Dividing both sides by negative 3, what do we end up with? X equals x. That's an odd solution. You could still, if you tried to minus x from both sides, what would you get? You get 0 equals 0. So this is that odd case, the middle one right here, but it end up being the exact same line that we're solving. This line ends up being equal to this line. So the answer to that would be infinitely many solutions. So we would write that out as our answer. Because we have 0 equal to 0, that is indeed a true statement. Infinitely many solutions. All right, let's take a look at the next one. Again, an equation equal to an equation. We have one side equal to the other, which again is just like looking at two separate lines equaling each other. These are fractions. I don't like working with fractions, so I'm going to go ahead and get rid of them. I'll multiply everything by 15. Why did I choose 15? Because these denominators here can all go into 15, so I know they can cancel. So that'll be 15 times the x over 5 plus the 15 times the 1 over 15 equals the 3x minus 5 over 15 times the 15. Now that 15 will cancel with that 5, just 3 left. That 15 entirely cancels, and this one also entirely cancels. So I am left with 3x plus 1 equals 3x minus 5. Ooh, that's a nice simple linear equation. So I'm going to go ahead, let's see, and get the x's on one side. And oh, look what happens. I am left with 1 equals negative 5 because the x's cancel out. Now before, the x's canceled out, but we had 0 equals 0, which was a true statement. But now we have negative 1 equals, we have 1 equals negative 5. Is this true? This is not a true statement. So the answer to this one is actually when they're parallel lines, and we would answer no solution. So the answer to this one, it comes out with an untrue statement, is no solution. Okay. Now, for example 3. Use the graph to solve each equation or inequality. So for part A, we're comparing f of x and g of x. Which ones are those? Well, g of x is this purplish red line, and f of x is this blue line, and we're comparing them. So we want to figure out when they're equal to each other. And when are they equal? Well, when they cross, and that is right here. And what point is that? That is 4, 3. So the answer to that's going to be 4, 3. And that is a point. Next, for B. When is f of x greater than 0? Well, remember, f of x, that's my y values. So let's look at the y values and figure out when f of x is above the horizontal axis. And that is for all of these values here. So from negative 2 to infinity, our y values are positive. So that'll be my answer. And this time it's an interval, not a point. Sorry, what was that? Did I say that was negative 2 up into infinity. Negative 2 to infinity. All right, and the next one, C. So when is g of x less than or equal to 0? Again, so what x values make the y values less than or equal to 0? So g of x is, oh, interesting. Is g of x ever ending up less than or equal to 0? This line is always floating above, so that never happens. So we would just say no solution. All right, let's look at g of x greater than 0. Let's see. Well, actually, remember, this line is always above 0. So it is greater than 0 from negative infinity to positive infinity. Okay, so we're writing the x values that make the y values whatever restriction that is there. So let's see, when is f of x greater than g of x? So that's going to be when f of x is larger numbers than g of x. So looking from left to right, if I read my graph, in the beginning, g of x is on top. But then, boop, it switches, and f of x starts being the bigger numbers, or greater than. So when does that switch occur? That switch occurs right here at 4. So from 4 and onward to infinity, f of x is greater than g of x. Next for f, when is f of x less than or equal to g of x? Well, that's pretty much the exact opposite of what we just looked for. Now we want to figure out when f of x is less than. And reading from left to right, when we start out, f of x is already below g of x. So we know f of x is lower or less than g of x all the way up until, boop, this point right here, which is still that boundary of 4. So f of x is less than g of x from negative infinity all the way up until positive 4. From negative infinity until 4, reading from left to right. So again, we answer in interval notation unless it's an exact point like a. And we're looking at the y values and answering with the x values that make that outcome for my function. Now let's take a look at example 4. We're going to be solving. What are we solving? Okay, these are a little different than what we've been working with before. These have the less than or equal to symbols. Okay, so we have to be careful. Again, a rule to note with inequalities is if you multiply or divide by a negative number, you need to flip the sign. All right, so let's go ahead and pretty much you solve these the exact same way you solve an inequality. Just be careful about multiplying or dividing by a negative. So I'll go ahead and multiply that in. That'll be negative 11x minus 6x plus 4 less than or equal to 3x minus 6. Combining the like terms on this side, and we get negative 17x plus 4 less than or equal to 3x minus 6. I'll add 17 to both sides, plus 6 to both sides, and we get 10 is less than or equal to 20x. And then lastly, dividing by 20. And simplifying that 20, so the 10 and the 20 cancel, and we're left with a half. X is greater than or equal to a half. Now if we were to try to graph this visually, what this would look like, I'll indicate where 0 is, and then a half, and x is greater than or equal to that. So it's all of these values above, and it's also possibly equal to. All right, moving on to the next one. Again, we have those fractions hanging out, so I want to get rid of them. So I'll go ahead and multiply everything by the greatest common factor, which is a 10. And then distributing in that 10, I'm going to skip some steps on this one. If you do need the inner steps, let me know with an email, but for now, I'm going to go ahead and skip those. So when we multiply in, it'll cancel those fractions, and we'll be left with 2 times x minus 2 minus 3x minus 5 greater than negative 20. Okay, I'm going to get rid of those parentheses, distributing. I have 2x minus 2 minus 3x minus 5 greater than negative 20. I'll go ahead and combine the like terms, 2x and 3x, and then negative 2 and negative 5. So I have negative x, negative 7 greater than negative 20. And then moving the x to the other, or the 7 to the other side, I'll add 7 to both sides. And I have negative x is greater than 13, negative 13. And lastly, we're going to go ahead and divide by negative 1 to get x by itself. Ooh, but when I do that, careful. I need to switch my inequality sign. Why? Because I divided by a negative number. And if you want to know the reason for that, again, just schedule an office hour with me and I can go over that as well. So now we have x is less than 13. And you could graph that as well. Indicate where 0 is and 13. And we know that x is less than, but not equal to. So we're not going to fill in that bubble. You only fill that bubble in if it's equal to, like we had on the other problem right here. All right, let's take a look at 5 and A and B. Ooh, what is different about these than the other ones? This one, I have two inequality symbols going on. This one's called a compound inequality. But don't worry, it's pretty similar to solving regular equations, except what you do to one of the sides, you do to all three. All right, so taking a look at this, where is my variable? It is on the inside. So my goal is to get everything that is not the variable on the other sides. So I know I need to get rid of that 9 and the 2. I'm going to go ahead and I'll divide both sides by 9, and I get negative 10 over 9, less than x minus 2, less than or equal to 4. Ooh, x is almost by itself. Just that 2 is keeping it. So I'm going to go ahead or add 2 to both sides. And I have negative 10 over 9, and I'll need to build up that fraction. So then let's see what's on the inside. X is just left, less than or equal to 6. So adding the fractions, I'll do the building up property, times 9 times 9. And that is going to be 8 over 9 is less than x, which is less than or equal to 6. Alrighty, and that is that. And if we wanted to graph that, just go ahead and show me where 0 is, and then plot your points, 8 over 9 and 6. And our answer is in between the two. It's equal to the last one, but not equal to the other one. Because this one doesn't have that line on the bottom, this one does. And if you want to answer in interval notation, just reading from left to right. Reading this way, our answer starts 8 over 9, not including, so I use that open parenthesis. And it continues until 6, boop, and then I do include 6, so I go ahead and use a bracket. And that's interval notation, reading from left to right. Now one last one. Again, it's a compound inequality, and we have x in one place. What's keeping x from being by itself? That 3, the negative 4, and the 2. So my plan, since they're all being divided by negative 2, first I'll multiply everyone by 2. But it's just a positive 2, so I don't have to worry about changing the symbols. This cancel. And I have negative 14 less than or equal to 3x minus 4 less than negative 4. I'll go ahead and add 4 to both sides. And I get negative 10 is less than or equal to 3x, which is less than 0. We're almost done. That 3 is just keeping x from being by itself. So I'll go ahead and divide by 3. And I have negative 10 divided by 3 is less than or equal to x, which is less than 0. Okay, so you can go ahead and box your answer on that. But let's go ahead and also graph it and then do some interval notation. So from negative 10 to 3 to 0. My answers are in between because x lies in between these two boundaries. And then it can be equal to the negative 10 over 3, but not to the 0. So my answer for interval notation, again reading from left to right, that's how we always do interval notation. We start at the negative 10 over 3 and we include it, so we'll do that little bracket. And then it continues until, boop, we stop at 0, but we don't include it. Alrighty, that is it for section 1.5. Please email me if you have any questions or concerns.